talking about waves, logistical things. This week there's no lab because there was no school yesterday. So no lab this week. But I will be here, so if anybody wants extra sort of office hour time, feel free to come to lab and you can ask questions, work on problems, come and go whenever you want, you know. You don't have to stay for 2 hours if you come, you know what I mean? All right. And we are now done with talking about harmonic motion, which means that any of the questions on the practice problems on harmonic motion, you're ready to work on. And now we're going on to talking about waves. So I did the drawing of the Frisbee and the guy on the shore. Does that work? Does it work to get your Frisbee that way? Okay, anyone remember why? Anyone give me a description of why? What? Yeah, right, the molecules aren't actually moving, just energy is moving from one set of molecules to the next one that's next to them. And then I gave 2 types of waves. I broke up waves into 2 different types. Anyone remember what that is without looking at notes? Yeah, otherwise that's not really remembering, you know. Okay, well, it has to do with 2 different directions and how they relate to each other. One is the direction that the wave is moving, and the other one is the direction that the molecules are oscillating. If the wave direction is this way, and the oscillations of the molecules are like this, that's called a transverse wave. So like water waves are transverse waves. I don't know what to call this, but like if you flick a rope or a cable or something, that's a transverse wave because the parts of the rope are moving up and down while the wave moves along the length of the rope. And sound waves are the other type, longitudinal, because what happens with the sound wave is your vocal cords or the speaker oscillate, and that gets the molecules oscillating this way, and then the next ones oscillate that way. And so the oscillation direction is parallel to the direction of the sound. So if you have the wave direction like this, and the oscillation direction is parallel to that, then that's called a longitudinal wave. And sound waves are an example of longitudinal waves. In order to picture the connection between vibrations and waves, or harmonic motion and waves is another way to say it. You can imagine like a simple harmonic oscillator like we were just talking about. So this thing is oscillating up and down, and imagine that it's connected to a rope. Well, as it goes up and down, it produces a wave in this rope, okay? And saying all waves are produced by oscillations seems like sort of a big statement. I'm not totally sure that's true, but I can't think of any counterexamples. So, I mean, I think it's fair to think that any wave is produced by some kind of harmonic motion, okay? Some kind of oscillation. Even light waves are produced by oscillations in something called a magnetic flux that we'll talk about later. And so even though it's not exactly like an oscillator like this, it's something oscillating, producing even light waves and electromagnetic waves. So, waves are defined by 5 quantities. And so I'm going to go through what these quantities are. So well, let me just list them out first, and then I'll go through and talk about them. So amplitude, period, frequency, wave speed, and wavelength. Not all of these are independent of each other. So, in other words, you can't pick values for all of these 5 and get a wave out of it. You know, for example, we already know from harmonic motion that period and frequency are different ways of talking about the same thing. So if you pick a period for your wave, then the frequency is already locked in, you know. But these are the 5 ways that people tend to talk about waves. So I'm just going to go through them one by one, talk about where those quantities come from. And I'm also going to mention what determines each of these things. So we're going to assume that every wave is produced by an oscillator, okay? So which of these things are determined by what the oscillator does? Which of these things are determined by the medium that the wave moves through, right? Like a sound wave moves through air, or, you know, if you make a noise underwater, it moves through water. So which of these things depend on the oscillator? Which of these things depend on the medium? And which of these things depend on both of those two? Okay. So first, amplitude. Amplitude is, you know, really you can think of this as, let me erase that. So if you think of a wave as oscillations of individual molecules, then the amplitude of the wave is the amplitude of those oscillations. And so if you think about it that way, then amplitude means exactly what it did when we talked about harmonic motion. Okay? Amplitude only depends on the amplitude of the oscillator if you assume no energy loss, which of course is an incorrect assumption, but that's an assumption that we're making in this class, and you can get good, you can get good approximations with that. One thing that's important about thinking about the amplitude is, let me say, for a wave in 2D or 3D, the amplitude of the wave has a more complicated relationship to the amplitude of the oscillator. Let's say the amplitude of the oscillator that caused the wave, that produced the wave. In 1D, a wave moving in 1D, this relationship is simple. If there's no energy loss, then whatever the amplitude is of the oscillator, that's the amplitude anywhere along the wave. Okay. So if there's no energy loss. So for example, if you had a wire strung across the room and you whacked it with a hammer, it would send a wave out along the wire. The amplitude that started that wave is the same amplitude that wave would have 5 feet away or whatever. So that's a 1D wave. A sound wave, for the most part, unless you're talking about a sound moving along like like if you hit a steel bar with a hammer or something, okay, that's a 1D wave. It's only moving along the bar. But if you're in a room talking, that's a 3D wave, right? Your vocal cords are oscillating. It's sending a sound wave out in 3 dimensions. And so for that, we'll talk about how to calculate this, but you have a more complicated relationship between the original amplitude of that sound and the amplitude far away. Okay. Second is period. So what do you think about period? Does that, you feel like that should depend on the oscillator, should depend on the medium? I think the easiest way to think about these is think about sound. What does the period represent in a sound physically, It represents the pitch, like how high, So like has a low period, has a high period. No, did I do that backwards? The low one has a high period, and I did those backwards, sorry. The low note has a high period, and the high note has a low period because I was sort of thinking of frequency. It's like this. So let me draw it. Okay, so a low note looks like that. If you're plotting position versus time. And so there's the period. Okay. A high note looks like this. And so the period for the high note is small. Okay. Okay, so think about like sound waves. You've heard sound waves when you've been underwater. You've heard sound waves in air. Do you have any feel for whether the period, in other words, how high or low a note is affected by the medium that it goes through? It's not actually. Why? Well, you could think of it this way. So the I lost it. If you think of sound waves, maybe this is a good way to think about it. Like what happens with a sound is like, say your vocal cords or the speaker, they vibrate, right? And that makes the molecules next to it vibrate, right? And that makes the molecules next to it vibrate. So imagine like a speaker underwater, okay? It vibrates, that oscillator, the speaker, still vibrates at that same frequency, right? So of course, that's the only frequency that it can make the water molecules next to it vibrate, okay? And then that's the only, you know what I mean? If you think of it that way, it sort of makes sense. Changing the medium, like
going from one medium to another medium.
Okay, so like a sound underwater and someone hears it out of the water or something. That changes some things, but it doesn't change the frequency.
What about when someone's like, you suck up some helium, and then the molecules are closer to the helium, which sort of changes the frequency of why you sound like you're
Yeah. So yeah, helium. What does that do? It that just makes your vocal cords oscillate in some different way. I think that's why it makes your voice sound funny. I mean, I think just the like the amount of airflow that you're used to going across your vocal cords, for some reason doesn't make them vibrate in the same way. But then once your vocal cords vibrate, everything's already set in motion, and then the frequency doesn't change. Okay. Any other questions about that? It seems a little odd, but yeah, I think at least for now, I think that way of thinking about it sort of makes sense. Like, just remember that all that's happening is little tiny balls are bouncing off of each other, you know? And so they're only going to oscillate at the frequency of the balls making them oscillate, you know? And so there's just chain reaction where nothing can be any other frequency but what the oscillator was. Okay, so period of the wave is the period of the oscillator that produces the wave. Third is the frequency. And just like with oscillators, the frequency is equal to 1 over the period. And the frequency of the wave is the frequency of the oscillator that produces the wave. Okay, so period and frequency are just two different ways of talking about the same thing. What this is saying is if you had a waterproof radio, first of all, and then listen to music underwater, the notes would all be the same. You know, the notes you hear aren't any higher or lower. Fourth is wave speed. We're going to write that as a lowercase v. And wave speed is a measure of how quickly a wave travels from one place to another. Okay, so wave speed is the speed of sound if you're talking about a sound wave, the speed of light if you're talking about a light wave. Anybody have a feel for whether that depends on the oscillator or the medium? Does it make sense? Well, in this sense, like you hear about the speed of sound and you don't ever hear like the speed of a loud sound or the speed of high-pitched sound, you know, like all sounds have the same speed. So in that sense, we're sort of used to talking about it not connected to an oscillator. The wave speed only depends on the medium. It only depends on what material the wave is moving through. In space, well, it depends on what kind of light. In space, there's no sound because, yeah, right, because sound depends on molecules moving around. The only wave that can travel through empty space is electromagnetic waves. So light can, and you know, light is just, electromagnetic waves, we have different names for a lot of different types of electromagnetic waves. And the only thing that changes is really the frequency of it. But like light, radio waves, microwaves, gamma rays, all those things are just different frequencies of electromagnetic waves. And those can all travel through empty space. So this one only depends on the medium the wave travels through. And this is, I guess, the first one that we're going to have calculations related to. So I'm going to give you a few different formulas for different types of waves. So the first one is transverse wave on a cable. So this is like the example I drew right at the start of this. So if you have an oscillator, more likely, you know, your hand or something, connected to a rope, as the oscillator goes up and down, it sends a wave along the rope. And the speed that this wave will travel along the rope is equal to the tension in the rope. So F sub T is the force of tension. Usually we write that just as a capital T, but I think we're writing it as a F sub T just so we don't get it confused with period here. And then divided by the mass per length. Okay, so, and the square root of everything. So what this says is if the rope gets tighter, the thing travels more quickly. And the denominator says if a meter of that cable gets greater, you have more material then the speed gets slower. Okay? So those are the only two things that matter. The tension and the mass per unit length. What are the SI units of wave speed? Yeah, meters per second. So it's about a wave, but it's still just a speed. The second type of wave is a longitudinal wave in a gas or a liquid. So here we're talking about sound waves. And the formula is the wave speed is equal to a constant written as a capital Greek letter beta. I'll tell you what these are in a second. Divided by Greek letter rho, like a squiggly p, and all square root. This beta, so this is the Greek letter beta, is called the bulk modulus. And it's a measure of how resistant the fluid is to volume change. Okay, so like for example, I don't know why I would think anyone would do this, but for some reason I've done it a lot of times, and I'm gonna assume that maybe you've done it at some time or another too. Like, have you ever, like, you have a glass bottle, like it's empty, a beer bottle or whatever, not you, but but Coke used to make bottles like this too. But anyways, so it's empty, and you put your lips against it, like try to, like, what am I thinking of? No, this isn't a good example of that. Okay, so do you have a feel for, oh no, here's a better one, Okay, so no, not a glass bottle. You have like a plastic liter bottle, okay, with the top on, okay? So no air can get in or out. There's air in there and it can't escape, right? And now you press it. Have you ever done that before? Like, you can imagine you can press it in a little bit, and then it starts to sort of resist, and then it gets harder and harder. What you're doing is changing the volume of air. You're not changing the amount of air, you're just making the air that's in there fit into a smaller volume. So you can do that with air. What about a new 2-liter bottle? that still has liquid in it. Can you compress that? You really can't. To the degree that you can do it, you're only doing it to the air that's in the top of the thing. And so the bulk modulus of air is very small compared to the bulk modulus of a liquid. That's all I'm trying to say. Didn't seem worth all that. Okay, and then rho. Anyone remember what rho stands for? So this is the Greek letter rho, R-H-O, and that is the density. And the density is equal to a material's mass per, mass per volume. Okay, so like steel has a higher density than wood does because the same volume of wood is lighter than that volume of steel. Okay, so from this, we're talking about sound waves in, let's think about it in air and water. Do you have a feel for which one is going to be bigger from this? Well, not really yet until we see some numbers, because you know that that for air, we're going to have a much smaller bulk modulus, but we're also going to have a much smaller density than water. So they're both going to go down, and as far as, you know, we don't know which one's going to go down more. But let's put some numbers to this and figure out what the speed of sound is in air compared to the speed of sound in water. So in air, you have a bulk modulus of 1.42 times 10 to the 5th pascals. The density is 1.204 kilograms per meters cubed. Take the square root and you get 343 meters per second. Okay, so that's the speed of sound at sea level. So now let's do it for water. The bulk modulus is going to go way up. So instead of 1.4 times 10 to the 5th pascals, we have 2.2 times 10 to the 9 pascals. The density of water is 1,000 kilograms per cubic meter. Yeah, that's a lot. So a cubic meter is big, you know, but that is, so from the table, it's like that tall, that wide, a cube. That's a ton, you know, that's 2,200 pounds. Yeah, right. And so you get 1,483 meters per second. So sound travels a lot faster in water than it does in air. And probably there's some way to exploit that for some kind of diabolical purpose. I don't know.
Yeah, let's try that.
Let's do that in lab. Yeah. Yeah, like some kind of dolphin, evil dolphin plot. We'll think about it more. And then the last type of wave that we're calculating the wave speed for is a longitudinal wave in a solid. So for this one, you can imagine like a steel bar and you just hit one end of it with a hammer, okay? So that signal That's going to be a couple of oscillations that are going to travel down the length, and that signal, we're going to calculate how fast it takes to get, like from one end of the bar to the other end. So for this calculation, the wave speed is equal to capital E over rho, square root. Rho is still equal to the density of the material. This capital E is called Young's modulus, or sometimes people just call it the stiffness, and that's what it's a measure of. How easy it is, really it's a measure of how hard it is to deform a material. So Play-Doh has a very low value of stiffness. Steel has a very high value of stiffness. The stiffest material is diamond. Okay, so for steel, Young's modulus, and this is just something you can Google this and it'll pop right up. 200 times 10 to the 9th pascals divided by its density, 7.8 times 10 to the 3rd kilograms per meters cubed. Take the square root of all of that, and you get 5,059.6 meters per second. So 4 times or something as fast as sound moves in water.
Would you say because the molecules will come back to each other? I'm not sure, like packed together?
Yeah, I think that's a really good way to think about it. Yep. The stiffer it is, the more sort of locked in place the molecules are, and so they're sort of forced to oscillate immediately when one oscillates. Yeah. Whereas, like the speed of sound goes down as the altitude gets higher, because you have fewer and fewer molecules as the altitude gets higher. And so getting one molecule to oscillate, it takes relatively like a long time until it contacts the molecules next to it. And so it just takes a while for that signal to transfer. Okay, so that's the end of wave speed. Yep.
How hard it is, what is it? The word is?
How hard is the material to deform? And so the last one we have to talk about is wavelength. The symbol for that is the Greek letter, I'm blanking on that one. Greek letter, lambda. Like lambda, 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 and omega mu. That's the fraternity in Revenge of the Nerds.
Oh.
It's a good movie. Like you're the only one who's probably seen that movie in here. It's getting, yeah. Gilbert in Revenge of the Nerds is my mom's second cousin. Yeah, I know. He also was Goose in Top Gun.
That's Gooch?
Yeah. I've never met him though. Okay, so the definition of wavelength is take a snapshot of the wave at a single instant. So at a single instant, it looks like this, right? And then measure from peak to peak. This distance is the wavelength. So what are the SI units for wavelength? Meters. It's just a measure of distance. This is something important to keep in mind if you're not thinking about this explicitly when you're looking at different graphs with waves. This can be really confusing. Wavelength and period look like the exact same thing, but they're on two different graphs. That's not how you spell there. So for the period, you're going to be looking at a position versus time graph. And then the period is the amount of time from peak to peak. Okay. For wavelength, you'll be looking at a position versus X graph. Like you'll be looking at a graph of the position in the oscillation versus the original position on the wave. That will also be a cosine function. And you measure this again as the distance from peak to peak. Okay, so you can see it, they look exactly the same. The way you can tell is, are you looking at a position versus time graph or a position versus X graph? Wavelength is the one thing of those 5 quantities that depends on both the oscillator and the medium. And there's one equation that we'll use for this. It's a relationship between between the wavelength and the wave speed and the frequency. So wavelength is equal to wave speed divided by frequency. All these equations are going to be given on exams. And this equation here can remind you that, that wavelength depends on both the medium and the oscillator. So this can remind you that wavelength depends on both the medium and the oscillator because the wave speed depends on the medium and frequency depends on the oscillator. So if you remember what those two depend on, then obviously if something that depends on the medium is in this calculation for the wavelength, and also something that depends on the oscillator is in this formula, then this has no choice but to depend on both of them. Okay. One example I sort of like that I forgot to mention when I was talking about wave speed. Another way to sort of make sense to yourself of the fact that wave speed is not affected by the oscillator is think of being at like an outdoor concert, okay, where you're like pretty far from the speakers, okay? If the wave speed depended on the oscillator, remember that music is just a series of different oscillations, you know, so some notes have a large amplitude and a high frequency, or a large amplitude and a low frequency, right? But the amplitude determines the loudness, the frequency determines the pitch. So if the wave speed changed when the oscillator changed, the farther you were from the speakers, the more jumbled the music would be, because like say the high frequency notes would get to you faster than the low frequency notes. And you know from experience that doesn't happen. And not very many people would pay to go to outdoor concerts if that happened. So, I don't know, I think that's a nice thing to just keep in mind to sort of remind you of this stuff. Any questions about any of these quantities? All right. Let's do a problem. So let's say that you have a cable that's, I have a hand there, it doesn't really have to be a hand, but let's say that something's making a wave move along this cable. And let's say that the cable's tension is 200 newtons. And let's say that the mass of the entire cable is 10 kilograms. And let's say that the length is 20 meters. Okay, so far we don't know anything about the form of this wave. we don't know anything about the, so we have stuff that'll let us calculate the wave speed along the cable, but we don't know anything about the oscillation that's causing this wave. So let's say that this oscillation follows this form. The position of like the hand as a function of time is equal to 0.1 times cosine of 10t. So 2 questions. First, how much time does a wave take to get from the hand to the wall? And second, what's the wavelength? Okay. Anybody want to take a few minutes and try to work through this stuff, or? Okay. Yeah, let's do that then. So let's take maybe 10 minutes, and then I'll do it in the last 10 minutes. See what you can get through. This is, you know, I would say for as much time as we've spent on waves and stuff, this is still kind of a fairly tricky problem. But this is the kind of thing that'll be on tests and in the practice problems. This just, it makes you combine a lot of the things that we've talked about, and that's what makes it tricky before you're sort of familiar with it.